claps. Welcome to the Amazing Physics Show. This is a show we put on, this is the second one we're putting on because it is only the third time that I've taught this class. It's a physics communications class at Trinity University called Speaking Physics. And we try to bring physics to the community as part of this class. And we have been working really hard this semester, especially for a 1 credit hour class, building a bunch of demonstrations for you in the makerspace and in our shop, and practicing delivering physics to you guys tonight. So without further ado, we are going to get started, and we're going to start at the beginning with Sir Isaac Newton. Isaac Newton formulated 3 laws of motion. And I'm going to bring Andra out on the stage to tell us about the first law.
Howdy, y'all. So I'm going to talk about Newton's first law of motion. You may have heard before the phrase that an object at rest will stay at rest unless acted upon by an outside force, and an object in motion will stay in motion unless acted upon by an outside force. And you know what? Actually, that's the whole law. I think I'm just going to have something to eat, have something to drink. I have a nice setup right here.
Hey, Andra, can I get that tablecloth for my demo?
Oh, but I already have all my stuff set up.
That's fine. I can just help you take the stuff off.
You know what? Actually, we just learned about Newton's first law of motion. I can just yank this tablecloth right off.
You sure about that?
Yeah, because these objects have inertia, also known as mass. And inertia wants to resist a change in motion. So if I yank out this tablecloth, only the tablecloth will move. The objects are going to stay there.
Ta-da!
Okay. Now we're going to skip law number 2 for law number 3. The third Newton law states that the force applied to one object has an equal and opposite force applied on the thing giving the force. To show this off, I'm going to have Reed here just kick me as far as he can. Okay? Whee! Now, even though Reed did not apply a force on himself and just kicked me, he was sent flying back as well because he was experiencing the same force on himself, just in the opposite direction. Okay? We're not done yet. Now, Reed here is going to have a heavy cinder block on him to demonstrate. Oh, yeah. Now, Newton's second law is force is proportional to the mass times acceleration. So that, just to quickly sum that up, a heavier object will tend to go faster when the same force is applied.
Slower.
Slower? Oh, slower. Okay, Reed, give me a launch. Whee! Again, I went flying. Reed barely went like a couple feet.
All right, so those are the 3 laws of motion. You may sort of keep these in the back of your mind as we continue the demonstrations this evening. Okay, so, let me spend a minute talking about gravity and the way that things fall near the surface of the Earth. Galileo did a bunch of experiments where he was tossing stuff off the Leaning Tower of Pisa, and he deduced that basically while the gravitational force gets stronger for more massive objects, you have more mass, gravity acts with a stronger force on that more mass. More mass means it's harder to accelerate too. So those two effects tend to cancel each other, and it turns out that all objects will fall at the same rate near the surface of the Earth, 9.8 meters per second squared.
Well, Dr. Mehta is a theorist, and he likes to ignore air resistance. But air resistance is important to how things fall. For example, when I drop this book and the feathers will fall slower, of course.
Our poor book. Good catch.
Just like the microphone
Alejandro
fell.
would kill us. Yeah, okay.
But if I were to put the feathers on top of the book to represent, to block the air that is getting pushed on the feather and the book should fall at the same speed.
So we're just going to block the air from reaching the feather. All right. So, I mean, it's tough, right? I mean, I always forget about air resistance because air is invisible. I can't see it. But, you know, it's important. It's all around us. It's this stuff, this physical stuff that is everywhere.
And it is important to remember that air is there. And when there is a lot of air, it's very heavy. So, at sea level, air has a value and weight of 15 pounds per square inch. So, at sea level, there is 15 pounds pushing down on every square inch of you. So, the more area, there is a higher force on you. To demonstrate, I will do a little experiment with this piece of wood. So, with the, I guess I do want the mic. With this wood, I put it on the edge, and when I karate chop it, I don't know karate, but it does exactly what we expect. It doesn't break, it just launches over here. But if I were to spread out this newspaper here, as Dr. Mehta is doing for me, it increases the area, which will in turn increase the force provided by air pressure. So, if we do this right, I hope it goes well. The air pressure supplies the force to break the wood into two pieces.
So what we're seeing here is that pressure is very important, and just to reiterate that, I want to show that with this bed of nails and some balloons. So first, what would you expect when you when you put one balloon onto one nail? It'll pop, right? And why is that? There's a small area that's being applied to this balloon with some force, and so the pressure is very high, and we see that it just pops. But what happens when we distribute that force, the same force, over a greater area? We see that the pressure is decreased, and so the balloon doesn't pop. And we'll see that this is very important to Dr. Mehta's safety later in the show with this bed of nails. So.
All right, what's Jake doing here? He's bringing something out. Jake, you want to tell us what's going on?
Yeah, of course. So thank you to Addison. And we want to pick up where we were talking about atmospheric pressure. And Reed did a great job of emphasizing how strong atmospheric pressure is. And so if you look at the screen, you can see kind of what we have right in front of you. You've got particles in the air all around, and then this bit of a barrel with particles inside
This box represents this room, and this represents the barrel, okay?
And so we have right here what's called a vacuum pump, and we're going to pull all of the air out of that barrel, and we're going to see what happens as it's going right now. And so you can see in here, what it looks like is there's no air inside the barrel to push out against the walls and keep the barrel stable. And so what's going to happen, hopefully in the next 5 to 10 minutes or so, is that this barrel is going to be crushed right in front of our eyes.
Hey y'all, so we know that atmospheric pressure is big, but did you know that pressure actually changes with the speed of the air? Well, fast-moving air creates areas of low pressure. This is called Bernoulli's principle. It's how airplanes fly. Ooh, we can start to hear that implosion. Let's get through this pretty fast. So you can see, you can see in the picture behind me that fast-moving air goes above the wing, which is an area of low pressure, and there's slow-moving air underneath the wing, which creates an area with more pressure. That's what has the lift that we see in airplanes. And if we go to the next slide, we can actually see a video of that. Now what I'm about to do is show you this effect called the shower curtain effect. So when I blow this leaf blower between two sheets, we're going to see them actually come together. And this is because the air that I'm blowing between them creates a region of low pressure, and the sheets want to go toward the low pressure.
Our vacuum pump is working.
The only thing getting them close to each other is moving air.
You may have noticed this effect when you turn on the shower at home, right? Your shower curtain comes in. It doesn't get blown out. And that's because the moving water from the shower causes lower pressure inside the shower. Okay, I think, air is just like everything else. It's made of atoms. 78% nitrogen, 21% oxygen, and about 1% other stuff. And just to illustrate that, Reed is going to try to knock down these styrofoam cups with this air cannon. It's tough to aim. We can't really see it. A little closer. Oh, that hit me in the face. Hey! Now, we might be able to see it better. No? Okay, well, let's listen to our drum. Does it sound like there's still air in there? Maybe. What happened to our top cup? Did we lose it? All right. Oh, it got stacked. Oh, no. It's like Jenga here. All right. Okay. So we thought that we would be able to visualize the air that comes out of this cannon a little bit better if we filled it with a little smoke from our smoke machine. So we're just waiting for that to warm up. So Reed, why don't you take another shot? Let's play a little game. How many guys think you can get it in one shot? 2, 3? 3? What's the over under on it? 3 shots. Let's go 3 shots. Reed, you got 3 tries. Whoa! All right. All right, let's see if I can do any better. Now this is a competition. All right, here we go. Okay. Okay, let's see what comes out of this thing. Woo! Can you go a little lower? Let's see if we can hit it. Those are pretty good. But those were small. Those were like little tiny smoke rings. So I was not happy with that rinky-dink thing I bought on Amazon, so I made my own. Let's see if we can get some big smoke rings here. All right. Okay, now I'm going to do one more. Yeah. Oh, that one was not so great. There we go. Okay, now I've got a little template here. You think we can make a square smoke ring? A smoke square? What do you think is going to happen? Let's put this over the round hole and see. Oh, it's still a circle. Still a circle. Okay, what about if we do the oval? What if we do the oval? What do you think is going to happen? You think we'll get an oval? Let's see. We get a jiggly circle. It's a jiggly circle. It's an oval one way, and then it jiggles to go the other way. So this kind of shape, when it is kind of jiggly like this, it's like I'm holding a steering wheel that's really flexible, right? And I squeeze it one way and it goes out this way, and then I squeeze it down this way and it goes out this way. Physicists have a fancy word for that kind of oscillation. We call it a quadrupole oscillation. And it turns out that gravitational waves that you may have heard of in the news also are a quadrupole oscillation. So gravitational waves that get emitted by neutron stars that combine, light years away and travel to the Earth and are detected by fancy gravitational wave detectors like LIGO. Those are quadrupole waves, just like you could visualize these jiggly circles. Okay, so at this point our vacuum pump is still working. Is there hope? We're not giving up. We're going to let it keep going. We're going to let it keep going. Let me see. I don't want to draw too much attention away from it, so let's see what we can get to next. So there is another way. So here we're pumping the air out, right? Nick has another method by which we can change the air pressure. Nick, you want to tell us a little bit about that? Yeah, you can tell us. We can start doing that too. We can bring it out. Let's just do it right next to the drum, so that we don't lose sight when this thing goes. Let me get you a mic. All right, safety first, right?
All right, so this is a cooler and is now empty, completely empty. What we have here, my assistant, will be pouring some liquid nitrogen into the cooler. Now, liquid nitrogen is very cold. Its boiling point is around negative 300 degrees Fahrenheit, or negative 200 degrees Celsius, which means if it's liquid, it better be colder than that. Go ahead. You can see it coming out, and a lot of it is already boiling. It's boiling just at room temperature. What I'm going to do is take a bunch of balloons and start putting them into the cooler.
What is air mostly made of? 78% nitrogen. And what's in there? Liquid nitrogen. So what do you think is going to happen to the air that's in the balloons? Yeah. It's going to shrink the balloons.
We're going to see how many I can fit in here. So place your bets now.
Okay, Nick is going to keep going. He's going to keep stuffing those balloons. And we're still waiting for this barrel, this drum. It's going. It's going. Our poor little vacuum pump, you can do it. Okay, if this doesn't go soon, I have one other trick up my sleeve. No. Well, we could use the same trick that's causing the balloons to deflate, right? If all the air in the balloons, which is mostly nitrogen, when it gets the same temperature as liquid nitrogen, it's going to want to condense into a liquid, right? Well, there's a bunch of air in there. Maybe I could reduce the pressure in there by dousing this with a little liquid nitrogen. All right, I'm going to try it. We're going off script here. We're cooling the air in there, trying to get it cold. Try to get the air in there to condense. Well, it's not working. You think we should just wait? What's that? No, it's sealed all. It should be tight. It should be tight. Otherwise, I would be hearing hissing. Okay. We're gonna move along, and we're gonna hope that this thing is gonna go. I'm gonna let it go. I'm gonna run it. Okay, so I think we can go ahead and try the beach ball. So we talked about the Bernoulli effect when we did the sheet demonstration, right? The shower curtain effect. Moving air is at a lower pressure than stationary air. So Andra and Sierra have another demo for you.
Yeah, so similar to what we saw with the shower curtain earlier, the leaf blower that Andra has over here is going to create a stream of moving air, which is going to have lower pressure than the surrounding air. So you're going to see when I put this beach ball over that stream of air, it's going to stay in the middle, and it's not just going to fall to the ground. So we're actually going to be able to levitate this beach ball, which is pretty cool. And that makes a little bit of sense when we're just doing it straight up, but what's really cool about this is that I'm going to poke it a little and it's still going to go back to the center, and then Andra's going to move it all the way over to the side and it's still going to stay hovering in the air. So let's try it out.
All right. Thank you, Andra and Sierra. Okay, so our barrel's still being stubborn, so let's keep going. So I want to switch topics a little bit and talk a little bit about what all this stuff around us is made of, right? Why can't you trust an atom? Because they make up everything. And in fact, so the atoms themselves are made of other particles, right? They're made of protons, which are positively charged, electrons, which are negatively charged, that zip around the outside of this nucleus, and the nucleus also has neutrons, which are neutral. And the key thing that I want you to remember here is that protons repel each other, they push each other apart, because they're both the same kind of charge. Electrons push each other apart because they're both the same kind of charge, both negative. But electrons and protons which are oppositely charged, they pull each other together. Okay? And finally, the last thing that I want you to remember is that that force, whether it's repulsive or attractive, gets weaker the farther away these two particles are from each other. Okay, so the closer they are, the stronger the force, the farther they are, the weaker the force. And V is going to demonstrate some interesting physics that's related to this. And I swear, if you did this back in the Middle Ages, you would be burned as a witch.
Yeah, so I have here a magic wand, also known as a small Van de Graaff generator. And what this Van de Graaff generator does is when I press the button, it starts running and pulling the electrons from this cardboard tube at the top, causing it to become electrically charged. And so, I believe we're going to take an intermission to take a look at this barrel now.
Keep going.
Okay. Here.
It's just moan. It's just moaning.
It's starting. But we're taking the electrons away from the top of the Van de Graaff generator, causing it to become positively charged. And when I bring it towards this lovely can of tea, you'll see that it begins to move. And it's pulled towards the wand. Mari, would you care to explain?
This is because, despite the fact that this can of peace tea is actually neutral, it's comprised of both positive and negative charges. And these negative charges are called electrons. And because this wand is positively charged, it draws the electrons in the can to the right side while leaving the left side positive, meaning that the attractive forces between the positive and negative charges are stronger than the repulsive forces.
So there we have our demo of electricity.
But why do we have to restrict ourselves to only the miniature Van de Graaff machine? Why not use a full-sized one?
Of course. So we have here a full-sized Van de Graaff generator, similar to with our wand. If we turn it on and begin to run it, this belt pulls the electrons from this top sphere and causes this sphere to become positively charged. And those charges cause these little hairs on the stand to polarize, and slowly they begin to stick up.
It went!
Oh my God.
Success! We broke the tube? No, it's still good. It's still good. It's still good. Okay.
I feel like I need something more visually impressive. So how about these pythons?
Okay, back to the Van de Graaff.
Back to the Van de Graaff. As a more spectacular demo, if we place these pythons on top and start the Van de Graaff generator again, they'll become positively charged and fly off.
All right. We also know that these pythons are made of aluminum, so they're going to be conducting, which means we pass the electrons, or the positive charge, that accumulates onto here, that accumulates onto the pythons, and once they get the same charge, then they repel each other. But did you also know that humans are conductive? To demonstrate this, we're going to ask our wonderful physics liaison, Mary Helen,
Mary Helen, come to the stage, please. Mary Helen, yay, Mary Helen. Okay, Mary Helen, we don't want to shock you with our amazing demonstrations. So we want you to step on the step stool. Step on the step stool. It's okay. It's okay. Yep. Now, I want you to put your hand on the Van de Graaff generator, which won't shock you. It's off. Okay. Now, do you want to wear a tinfoil hat, or do you want to just hold these?
It doesn't matter, however.
Let's hold them. Hold them in your hand. Now we're going to turn this on, and you're going to get charged up. Don't take your hand off, okay? You're going to get charged up, and these electrons are going to flow through you.
There we go. Yeah.
Are you magic, Mary Helen? Can you levitate
Levitating
pythons?
pythons?
I did that.
Didn't tell us you had telekinesis.
Okay.
You need to charge it. Hold on, don't take your hand off yet. Okay, charge it. Go ahead. Go. Okay, I just don't want it down on the bottom.
Now you can take your hand off for now.
Yeah.
No, you can take your hand off.
Can I get off?
You can step off.
Yeah,
All right.
you're good to go.
Thank you.
Let's give it up for Mary Ellen. Nothing we do in the physics department would be possible without Mary Helen. She takes care of everything for us.
Okay, what do we have after? Is that the last minute? I think so.
Better? You guys hear me better? All right, good. Okay, thank you. So I want to show you one other demonstration here. These are called the Franklin's bells. Benjamin Franklin had these installed in his house, and I found this curiosity just so enchanting that I had to make my own. And the idea was that he would have this metal rod, this brass rod, which is connected to this bell. This brass rod was then connected to the lightning rod in his house. There's a clapper here that hangs from an insulating string. It's just a little soda can tab that I've taken off. This bell is grounded. So he has a wire, he would have a wire just going to ground on that bell. And when there's an electric storm, the lightning rod would accumulate some amount of charge, and that would cause this bell to be charged up. That causes the clapper to polarize and is attracted to this bell. The clapper then acquires some of the same charge that the bell has, is repelled from the bell, and pushed to the other bell. It deposits that charge on that bell and becomes neutral again, and the whole process repeats. So the bell would start ringing when there was a lightning storm going. Okay? So if I turn on the Van der Graaf generator, we should hear the bells begin to ring. So let's do that. I'm going to turn this on. Okay. Can you guys hear that? Let's get the microphone a little closer. All right, and then presumably at this point, Ben Franklin would run and grab his kite and go out into the storm and do some more experiments. All right, so those are Franklin's bells. So let's check on our balloons. Nick needs a mic. All right, let's check on our balloons. How many balloons? Did you guys make a guess as to how many he's going to have in there? Were you counting? That's very specific.
All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That looks like that's it.
They still cold? Ooh, they're still a little cold.
Look, the ones that were all deflated are starting to reinflate again as the air warms them up.
All right. So yeah, the air warms them up. The liquid that was in there now is turning back to a gas, a nitrogen gas, and it's inflating the balloons again. Okay. Thank you, Nick. So I want to spend a quick minute talking about what happens. We learned about electrical charges, right? Positive charges and negative charges. I want to spend a minute talking about what happens when you jiggle a charge, okay? When you jiggle a charge. So here's a positive charge, and it's emitting these things called electric field lines. They radiate outwards from a positive charge. If the charge is stationary, they just kind of are straight, but as soon as you grab the charge and you jiggle it back and forth, the lines become kind of wavy, right? And these waves propagate outwards. Back in the 1800s, a gentleman by the name of James Clerk Maxwell thought very deeply about these waves that emanate away from these jiggling charges. And he showed in a remarkable paper that, in fact, the waves move at the speed of light. And that's no coincidence. He deduced that those waves, when you jiggle a charge, are in fact light itself. That is what light is. So it gives me shivers down my spine to think about this. Everything you are looking at, every color you see, all of the light you see around you is light that traveled to your eye from something, some object, right? That object has a jiggling charge, some electron jiggling back and forth that's radiating this light towards you until it reaches your eye. That is what light is, a wave in the electromagnetic field. The waves that we see are rather limited. Here is the electromagnetic spectrum. The only thing that's different between visible light that you see and all other forms of waves that come off this jiggling charge is the frequency or the wavelength, right? We can only see a narrow band of frequencies from this purple to this red, right? And that's all we can see. Now, there are all kinds of other wavelengths here. In fact, actually, can I have Addison out here to show us the spectrum in real life? Can we get a spectrum on the screen here? So we have a bright light source somewhere. What do we do with that? Yes. So can we get the lights dimmed here on the stage just a little bit, please? So we're shining this bright light through this diffraction grating, which kind of acts like a prism. And you can see the white light goes straight through, but off to the side, there's a rainbow. So we've taken this white light and we've split it into all of its different colors that comprise white light, okay? And I think that's pretty remarkable. The human eye can kind of only it only has three color receptors, right? Red, green, and blue. And we use those to distinguish between these various colors. One other thing I'd point out is that the light doesn't always go in a straight line here, right? There's one spot that's right straight, but then the colors went off to the side. Light followed a crooked path when it got separated into those colors. Okay, so I think at this point we have some other consequences of electromagnetic waves. I want to point out that one of the bands of electromagnetic radiation that you see here is very hard to read, is radio. Radio. There's a reason we call radios, because they pick up radio waves, which are just another form of light. It's just light that you cannot see.
Indeed, and so here I have a little portable radio, taking some AM, and if we tune it just right, you can hear that we're picking up the news. However, when I take this radio and I place it inside of this box with the mesh, it goes perfectly quiet, even as I move it around. And if I take it out, nice and loud, put it right back in, close the door, and it's quiet.
What do we call this, V?
And so this box is called a Faraday cage. It is named after Michael Faraday, who I believe we will be seeing a bit more from in the future.
Yeah.
And the reason that this works is the radio waves, the electromagnetic field of the radio wave, causes the electrons in this mesh to move in such a way that it perfectly cancels out all of the radio waves coming in. And so inside of this box, there are no electric fields.
Yeah, the electric fields don't penetrate. It's like the radio is completely unaffected by whatever is going on outside the Faraday cage.
Isolated.
Thanks, V. Okay, I think Andra has some additional
Yeah, so we've
knowledge
talked
for
about the
us.
fact that light is a wave, right? And the color of light corresponds to the frequency of the wave. Well, there's some really interesting things about colors. Y'all have probably seen something like this before, some kind of color wheel. Well, one interesting thing about the way that we see is that we can only actually see three colors. We can see red, green, and blue. And all the other colors we kind of like make up in our mind as a combination of those colors. And so I'm gonna demonstrate this with light. And the way I'm gonna do this is if we could please have the lights, all of them down. We have a few different colored lights here. We have all of them. There we go. There's 3 lights. They're playing around in a dark room. Very fun. So what happens if the blue light crosses over the green light? Yeah, it turns cyan. Awesome. What happens if the green light goes over the red light? Exactly, it turns yellow.
You guys are a bunch of ringers. What's going on?
Then what happens if we cross the red and the blue light? Well, everyone already knows this demo, so I guess I don't have to do the next one, right? What happens if we combine all three colors? That's a lot. Oh, blue is running away. Come back, blue. No. No. There we go. All of them mix white. Well, this is what happens with light bulbs, or with our flashlights. Sorry if I shined you, that was my bad. This is what happens with our flashlights. But I really want to prove to you that this happens because of our eyes tricking us. Yeah, so we have these wheels right here. The ones on the top aren't going to move. The ones on the bottom we're going to spin up really fast. And I want to show to you that, let's say on the far right here, we have a red and blue colors. If we spin them up real fast, we're going to see them make magenta. And that's not because they're actually combining. It's because our brain is tricking us into seeing the red and the blue so fast that we see them together as magenta. So let's find the right cable. Just plug them both in. They're going to start spinning really fast.
Oh, we're missing one.
No, it just, cable got stuck. That's pretty cool, right? On the top, we can see what it used to be. On the bottom, we can see what happens if we spin it up. That's just your eyes. Now, we have one more wheel up here, and that wheel has all three colors I said we can see. And what did I say before when I said when we cross all three colors, we get what? Exactly. So what do we think is going to happen when I start spinning this up? If it turns on. There it is.
Wait. Oh my gosh!
All right.
Awesome.
This motor is making me nervous.
Yeah, the motor's a little bit found in the closet. Don't worry about that.
Just the death throes of our old motor.
Object in motion stays in motion. It just kept spinning.
Okay, let's give it up for Andra and her fabulous color mixing demo. Next we have Marco, who's going to tell us about some pretty neat stuff.
All right, who has heard of Pringles? Who likes Pringles? I like Pringles. Does anyone know why Pringles are shaped the way that they're shaped? Want to take a guess? Yeah, they're thin pieces, so they break easily. And the Pringles were shaped that way to make them be able to pack more in a small space and for them to not break so easily. Something interesting about the Pringle shape, though, is that it's mathematically called a hyperbolic paraboloid. And what I have here is basically a hyperbolic paraboloid. It's just cut off a little bit on the edges. And at the center of this hyperbolic paraboloid is something called the saddle point. So we see that horse saddle. That's because it kind of has the same type of shape as this central point here. So something interesting we were talking about earlier is a Faraday cage, which is something that blocks in the flow of radio waves. But in this case, we have something a little bit different. We call it a classical analog to an ion trap. We were told in physics classes that there's no way to trap electrons with static electric fields. Can we get next slide? The only way to trap an electron with a bunch of electric fields is to make dynamic fields hold them in. So we can see here, this is like a saddle point that twists which direction it's oriented. And that's the only way we can hold an electron in the middle. But because we have access to one other little force all the time called gravity, we don't actually have to make this twisting field anymore. We can actually rotate the field. And that's what I'm going to have Dr. Kelton come up and show us demonstrate. So if we imagine this ping pong ball as kind of like a charged particle, like an electron, but rather it's repelled by the surface because it's just interacting with it physically. When we spin up this field, instead of it rolling right off like it does this time, because it'll always roll downhill, when we spin it up, we're going to end up seeing it kind of oscillate its way towards the middle. Now, these balls, the ping pong balls, have some friction against the surface of the saddle, so they don't stay on forever, but they stay on way longer than we would if we weren't spinning it. So come on up, Dr. Kelton. So it might take a tiny bit of tweaking with the current to make sure we get the right rotation rate. But I'll ask Dr. Kelton to take some of these ping pong balls and drop them somewhere near the center, and we're going to see them kind of stay on a spookily long amount of time. So let's go ahead and turn this on. All right, let's get an activation voltage. Oh, that's too high. Sorry, hold on. Okay, go ahead. Yeah, try to not to let it bounce. Try to get it near the surface, yeah. There we go. Oh, let's get another one. Oh, go ahead. Look at that. So what's happening here is that as the ball is rolling around the side, as it starts rolling its way down the hill, the side that's sloped downwards, the upsloping side ends up catching it just in time to push it back towards the center, basically creating a stable equilibrium near the center. Thanks.
Thank you, Marco. Next we have Alec. Alec, what do you have for us?
Hi there, guys. Do you guys remember a little bit earlier when we talked about Michael Faraday and this Faraday cage on the right-hand side of me, your left? Well, it turns out that Michael Faraday contributed a lot to us, and one of those things is something that we call Faraday's law, or Faraday's rule. And what it tells us is that we can use a changing magnetic field to create an electric field, or a changing electric field to create a magnetic field. And we can use that in a lot of ways, and we love to do so as physicists. Next slide. And one of the main things that we like to do is send current through a loop of wire. And if we send current through a loop of wire, we can actually create a magnetic moment, or essentially just a magnet, facing in a direction that's dictated by the counterclockwise or clockwise direction of the current that's running through that wire. So what I have here is purely a device that will run current around this wire and create essentially a magnet that faces upwards. And whenever I make that magnetic field by running that current through a wire, it actually will create an opposing current in another loop of metal that is around it. And that opposing current will actually create its own magnetic field. So if I take this little loop of metal and I stick it around this coil and I run current through this, I will essentially put current through this loop of metal, and by doing so, it will create its own magnetic field and will repel from this loop because of the fact that it is creating a magnetic field that's opposite the magnetic field that this coil creates. And we know that opposite sides of magnets repel, right? So what I'm going to do is I'm just going to turn on this coil, and a bunch of current is going to go through here, and you're going to see this loop fly into the air. And just like that, it goes all the way in the air, right? So we can also try and do this with a slightly heavier piece of metal, but this metal is copper, so it has a slightly better conductivity than the previous metal I used, but it's also much heavier, so is it going to go higher? Not quite. Turns out it's a little bit too heavy to go higher. But what I can do is actually get something else here. This is a slightly more conductive metal than the first one I used, but it's also still quite light. And this one, oh, can't catch it every time. That one went nice and high, right? We've got one more thing here before I show you the last part of this. And this is just a little ring of metal that isn't quite complete. There's a slight gap taken out of this. I don't know if you can see it. And as a result, when I put this around my coil, it turns out I won't be able to get a full circle of current going through it. And because I can't get a full circle of current going through it, I will have no ability to actually make a magnetic moment in this. So it's not going to fly anywhere. And we do in fact see that. It doesn't go anywhere. And lastly, I can put a light bulb around this coil. And this light bulb has its own coil built into the back of it. So it will create a small current that's flowing through that coil right there. And what's going to happen is this light bulb is going to turn on. And as you can see, it turns on.
This, by the way, that is exactly how those wireless phone chargers you have work.
This is
the same physics.
This is the same concept by which your phone charger might charge your phone wirelessly, and it's also a relatively similar concept to how an electric car might store energy as you brake your car.
So there's one other thing, right, Alec?
Yeah, we have one more thing that we can show you with this, and that is if we take this metal ring and we cool it down a bunch by sticking it into this freezer of liquid nitrogen that we had from earlier, it's going to get nice and cold. And there's one thing that we know about metals when they get cold. It turns out their conductivity increases. So do you remember earlier when we shot that piece of copper up, it might have went about this high or so? Well, now, if we take it really cold and we stick it on top, it goes slightly higher.
Let's get it colder.
We can get it a little bit colder and maybe get it even further. But essentially by lowering that or increasing that conductivity, we can get the current to go faster and larger, essentially. And by doing so, we can create a larger magnetic field. And if we get a larger magnetic field, we get a larger repulsive force. And we can, in theory, get this thing going pretty high. Although it does depend on how cold we can really get this copper. And we're sort of at the very ends of our liquid nitrogen here.
Oh no, it's working. We got it. We got it.
Okay, let's see this. There you go, that's a little bit better. Oh,
A little bit higher.
Sorry,
Let's try this one.
Don't want to catch it, it's a little bit cold. Oh, that one's good. That one's much better.
All conductors become better conductors when they're colder. Okay, so I want to talk a minute about resonance. So we have here a slinky, and I think we have a couple of volunteers who will demonstrate. So Addison and Sierra have this big, long slinky. Now, Addison, can you send one quick pulse to Sierra and then back? Okay, cool. So one thing I want you to notice is that the pulse goes down, and then it reflects. It's inverted, and then it comes back. It's going to reflect again, invert, back to upright, and then go back and forth, right? So it keeps flipping every time it reflects. Now, if Addison times it just right, he can create another wave that adds to the one that came back and reflected. And you can get a bigger wave, right? If he oscillates just at the right frequency, you get what's called a standing wave. This is what you get when this blue wave that's moving to the right adds to the red wave that's moving to the left. You get a wave that doesn't look like it's moving at all. It's just standing. It's oscillating up and down. Okay? And you have these points called nodes that are parts of the wave that don't move at all. This is a node. Okay? This is a node right here. And this is what we would call the second harmonic of this slinky. And let's see if we can get the next harmonic or the one after. We have to oscillate faster, right? Yeah. You think we can get one more? Yes. Awesome. All right. Thank you, Addison and Sierra. So if you go to Parker Chapel or something, we have a huge organ. My colleague Oren Schindel made this little flute, which is made out of a pipe. And when you blow this little flute, it sets up a standing wave, just like the standing wave we saw on the slinky, but it's a standing wave of sound. Okay, so that's how these things work. And you can hear the sound. The frequency that you hear is exactly the frequency at which, if you imagine Addison jiggling that slinky. It's the same frequency, it's the same phenomenon. And here we have a curious, this pipe is driven by me blowing into it, and there's some complicated physics associated with this little slot. But these pipes are a little different. These are thermally driven. So what I'm going to do is I'm going to heat this wire mesh that I have positioned in this glass tube. It's really just a glass tube. There's a wire mesh in there. We're going to heat this up, and that is going to drive a standing wave in this pipe. Okay, it's going to draw in, when I hold it vertically, it'll draw in cool air from the bottom and create a standing wave. If I hold it horizontally, it can't draw in any cool air from the bottom and the sound will stop. Okay, so let's hear that. Let's try it again. All right, we have two of these, and they're a little bit different. What's different about them? One of them's a little shorter. And so its frequency is going to be a little different. And if you've ever tuned a guitar and the two strings are a little bit off, you hear these little wah, 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 wah that we call beat notes. Okay? So that's what these are going to do. We have two frequencies they're going to resonate at, and it's a little bit different. It's just like having two guitar strings that are just a little bit off tune, right? And you listen, when you tune a guitar, what you do is you make those wah, 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 wahs longer, wah, wah, and then you know when they finally go away that your guitar is in tune. So let's drive both of these and listen for the wah, wah, wahs. Those are the beat notes. Those are the beats. We call them wah wah wahs. So this phenomena of resonance is ubiquitous. It really occurs everywhere. We've just heard it in sound. I want to show you one other example. Here we have an oscillator, which is just a tuning fork. Okay, it's just a tuning fork. And if I strike the tuning fork, it rings. Okay? This tuning fork rings at 132 hertz. Now what I'm going to do here, I have another tuning fork, exactly the same kind, also 132 hertz. When the sound that's emitted from this tuning fork vibrates in the vicinity of this box, it's going to be coupled directly to this tuning fork. And this tuning fork, because it likes that frequency, it resonates at that frequency, it's also going to start vibrating. Now, the vibrations are pretty small because the coupling is small, but you should be able to see it because I have a ping pong ball resting right here on this tuning fork. So you should see when this one starts vibrating is this ping pong ball starting to bounce. Okay? It's a subtle effect, but I think we should be able to do it. Let's see it. Okay. Okay, so there's a resonant transfer of energy. Energy from this tuning fork is transferred into this tuning fork. Okay? And these oscillators come in all kinds. This is a mechanical oscillator. But we also can make electromagnetic oscillators, okay? And so that is precisely what we've done. We've made a very special electromagnetic oscillator. We've made two, and they resonate together. One of them we call the primary circuit. The second one we call the secondary circuit. And energy is transferred from the primary circuit to the secondary circuit. So at this point, I'm going to hand it over to Omari and Alec. And they're going to talk about Nikola Tesla.
Has anyone in here ever heard of Nikola Tesla? Well, he's this handsome gentleman right here, if you didn't know. He was a Serbian-American inventor, electrical engineer, and futurist. And he spent much of his life's career trying to create wireless electricity. In doing so, he accidentally found radio waves and thought they weren't interesting enough. Made AC current, also thought it wasn't interesting enough. And so then he started focusing on things like this. But he really had three loves in life. The number 3, he'd love this list, pigeons, which he would routinely spend hours feeding in his hotel room, and electricity. So he'd create giant Tesla coils, which he could create room-sized electrical sparks with. And he was so fascinated by this idea that he spent much of his later career creating a massive tower-sized Tesla coil at Wardenclyffe Labs, which he hoped to power an entire city wirelessly. And unfortunately, it didn't work. But we've created our own. And I'll let Alec here explain it.
Okay, so we talked a little bit about resonators earlier, and we also talked a little bit about Faraday's law, where we realized that a changing magnetic field can create an electric current, right? So it turns out if we take two coils and we put a current through one of them, it'll create a magnetic field. That magnetic field can then make a current go in another coil that's right next to it. And if they're perfectly tuned so that their resonant frequencies of both of those two circuits are on with each other, then we can drive a lot of current through both of these. And what we've done is we've essentially created a series of two of these systems, which we call transformers. On the left side of our screen, for the astute engineers among you who would like to go home and build this stupidly complex circuit that we spent many, many months making, you can just read this circuit off quite easily. We have a transformer on the left that takes our wall outlet, which operates at 110 volts, and it multiplies it up to 15,000 volts. And afterwards, we take this second circuit on our right, and we up that to 600,000 volts. Unfortunately, we can't quite get to the levels that Tesla was getting, which were near 10 million volts, but 600,000 is still pretty good for us, considering that we made this in the workshop that we have in the last couple of months. So, what we're going to do is we're going to charge up this large capacitor that's on top of the circuit diagram right here. It's relatively unimportant if you don't know what it is, but it's a pretty cool thing that we spent many, many hours making. And then we built the rest of this circuit around it, and hopefully we can get both of these resonators to resonate with each other, and we can create a large spark of lightning between these 2 points. And how does that work exactly? It's pretty simple, luckily. If we have a large electromagnetic field, where we have 600,000 volts, that might just be enough, we can strip the electrons off of air. And if we can strip the electrons off of air, we've made the air into a conductor. And then we can pass current directly through the air without much resistance whatsoever. And what does that look like? It looks like lightning. So let's see if we can get the lights down, please, and then we can take a look and see if we can get a nice spark going.
Now, like I said, Tesla was very invested in getting these to provide wireless electricity to devices across entire cities. And while neither ours nor his could accomplish such a feat, we can show you that the principle behind it still stands. If we could get the lights turned off once again. The other side. Alec here is holding a fluorescent light bulb. Due to the electric field created by this Tesla coil, the terminals on the end of this fluorescent light bulb are able to power.
All right. Thank you very much, Alec and Omari, for your hard work. We spent many hours on this. And now it's time for a little game I like to call Which Way Will It Roll? Is it the right way? Let's just get this through there. All right. Okay, so here, I have a spool, okay? I've got a spool. And now, Jake here is going to help me do this demonstration. He is going to pull, now right now the spool has an outer radius and an inner radius, and there's a rope tied around this inside of this spool, right? He's going to pull, it's tied around this way, so right now the rope is going over the top of the spool and you know, kind of draped out in that direction. Now Jake is going to pull in that direction. He's going to pull that way, okay? And I want you guys to think about this. You're gonna talk to your neighbor, talk to your friends, talk to your parents. Try to decide which way the spool is going to go, okay? Okay, if you think the spool is going to go to the left, say left. Left. Okay, if you think the spool is going to go to the right, say right. Right. Okay. Okay, let's show him, Jake. All right, it goes to the left. Good job, good job. Now, next question. Next question. Well, okay, let me say this one. There are two forces acting on the spool, right? There's the force of the pull, and there's also friction, because friction with the floor acts on the bottom of the spool. In this case, both of those forces point in the same direction, so it's not too surprising that the spool goes to the left, okay? Okay? All right, now, what happens if we pull up? Again, take a minute to think about it. Talk to your neighbors. Oh, yeah. Okay. If you think the spool will go to the left, say left. Left. If you think the spool will go to the right, say right. Right. Okay. If you think the spool won't move at all. No? Say no, say not at all. Wow, okay, a lot of controversy on that one. Okay, let's do the experiment. Okay, it goes left. It goes left. All right. Now, last question. Last question. We're going to now pull this way, okay? We're going to pull this way. All right, now the string is coming, the rope is coming underneath the spool, and we're going to pull this way, okay? Now, think about it. All right. If you think the spool will go to the left, say left. Left. If you think the spool will go to the right, say right. Right. I don't know who won. That's controversy. That's how science is done. We now do the experiment. Yeah. Okay. Ready? It winds up the rope. It goes this way. How many of you guys were surprised by that? Yeah. When I first saw this demonstration, I was surprised. I said it would go that way, and I was honestly surprised. And that's why I love this so much, because physics is about just like little surprises like this. This is a simple system, right? I can't imagine anything much simpler than this, and it gave me a surprising result. Now, if I pulled this way and it went this way, but we pulled up and it went that way, that means there's got to be some angle at which it won't move at all, right? Let's see. Right about there, right? If I pull this way, it comes. If I go up, it goes that way. But there's an angle. If I pull, the darn thing won't move. Okay. Thank you. Okay, so I'd like to bring Addison back onto the stage to tell us about center of mass. Now, you guys might have seen this this viral sort of social media thing where there's a man and a woman, and you know, they lie down like this, they go down like this, and then the guy has to do this, and he just falls on his head, right? But women can do that. Women can do that. That's because their center of mass is a little bit lower down on their body, and they can be more stable that way.
Yeah, so the center of mass is basically the point on any object where we can consider all of the forces acting at that point. So if you look at the seesaw up here, the point right at the center of the seesaw is where that center of mass is, and that's where we put that pivot, is right at the center. And so we can do some interesting things by just moving the center of mass by distributing mass in different ways. And so here in this simple system, right, originally the center of mass when we hold it straight out is right here on this board, right? And so what do we expect? The only force that's acting on this board is gravity. So what do we expect to happen? Right, the center of mass just falls straight down and it kind of like rotates this way. But now we're going to do something interesting with the sledgehammer, okay? We're gonna change the mass around. We're gonna change this mass distribution around.
What if I told you I could attach this sledgehammer to this board and it won't swing down?
No. It won't.
Here I go. I'm going to use this rope and I'm going to attach it just like this. Hang on. It's really heavy. And it's stable.
Yeah, we can put things on the side to make it stay, and it'll stay standing right where it is. So what's happening here is the center of mass lies on this side of the, this side of the.
We moved it.
Yeah.
We moved it. Before it was here.
It was here, and now
it's over here because this thing is so heavy.
And so now when we push this up and down, right, the center of mass, it's moving up and down like this, but it wants to go back to that same point. So when we move it, right, when we're pushing down, gravity wants to bring it back to that point that it was. So the center of mass is keeping it in this steady position. Or gravity's keeping the center of mass in this steady position.
So this board is stable. I liked this demonstration so much that I made a different one as well. And I'd like to thank my daughter Rosa for letting me take apart her old bike that she didn't use anymore. So I took apart her bike and I made this curious unicycle. This unicycle is self-balancing. It's just sitting here on this rail, okay? Where is the center of mass? Well, okay, it's a little finicky. These poor little guys are not so. They've seen better days. All right, here we go.
Pull the one to the right. Yeah.
All right. So.
Wait, push it in actually.
So if we balance it just right, the center of mass should sit right below the rim of this wheel, and it won't move at all. Okay? Ta-da! Almost. Oh, it's not so stiff anymore, huh?
Can you pull it out of the?
It won't stay.
Okay.
There we go. All right, let's try it. Okay. All right, can I try? Yeah. Unfortunately, this pipe is a little bit broken.
Can I balance it with the wrench?
There we go. Okay. Almost. Okay. So, if we do this right, I should be able to send this whole unicycle down this slack line. I hope it'll work. This pipe is kind of fraying here, and it might lose integrity. Losing integrity, Captain. All right. All right, Addison is going to be ready to catch it if things go sideways. Here we go. Ready? Almost.
You want to show it just on the slack line, maybe? That'd be. I also have I got the.
Here. Let's grab this.
They're all here.
I got it. All right. Yeah.
Put this on.
I'm not sure it'll make much difference right now, but we can try it one more time. Okay, ready? Yeah. All right, still pretty cool, I think, but unfortunately this pipe is about to break off. So we're gonna have to rebuild this guy. Okay, thank you all for your patience with that one. Now, what did I do with the, here we go. Okay. Okay, so that's center of mass. Now,
Actually, about how rolling is a really good way of demonstrating the first law of motion. I go all the way across this, and unless there's an outside force acting upon me, I don't stop. My momentum is completely conserved.
So Andra just gave us a great look at linear momentum, and she was just going one direction. But something interesting happens also when we have a spinning thing. And so Nick here, I hear, has really gotten into ice skating recently. He's starting up a career, trying to go to the LA Olympics in 2028, right? Except those are Summer Olympics, so yeah. Well, anyways, Nick is going to show us some of his skills with doing his twist here. And so what happens is, as Nick spins, he has angular momentum, and it's going to want to be conserved just like Andra's linear momentum. And what happens is, instead of looking at mass and linear speed, we're going to be looking at Nick's, you probably want to spin him with his arms out.
Or we're just showing them.
Okay, sorry. So what happens is Nick has a moment of inertia, and that's basically the same as mass. And when he moves these weights out, his moment of inertia gets larger. And when he brings them in, it gets smaller. And so when he's spinning, he's got a certain amount of angular momentum here, and it wants to be conserved when he brings his arms in. And so his speed has to increase to account for the decrease in angular in his moment of inertia.
All right,
give it up for
Nick.
Professional ice skater here. Wow.
All right, all that's undone.
Okay, that same line of thinking though, we also have another example of angular momentum trying to be conserved. And the question here is, do we have any idea what a gyroscope is? Does anyone know what that is? A gyroscope is a way of showing conservation of angular momentum and also maybe some of the behaviors of torque. So before we spin it, let's drop it first. So if we hold this wheel out by this rope that's connected on the handle, if we just drop it, it'll fall straight down like we would expect. It'll dangle free, there's nothing to hold it in place. But a little bit more interestingly, if we spin it up, Nick will spin up the wheel, we can hold the rope and the wheel will stay up. That's very spooky. That's like anti-gravity type of spooky. But you also notice that it's doing something, it's spinning around this rope piece. That's called precession. And precession happens when, wow, I just stubbed my thumb really hard. Do you want to try spinning it one more time? Yeah, it's spin down. So precession happens when we have an external force being applied to this spinning object. So in this case, you can drop it down. Yeah. In this case, we have the rope holding up the actual handle, but gravity acts on the center of mass of this object. So gravity is acting in the direct center of that handle. And so gravity is pulling down away from the axis of rotation. So we can see the spot where it's rotating from is this rope piece. So we're going to learn something very short called the right-hand rule. And the right-hand rule tells us that if we put our hands or our arms in the direction of the radial arm, right? So from the rope out to the center, if I put my arm that direction, and then I put my hand, tilt it towards the direction that gravity is pointing, which always is down, my thumb ends up pointing in the direction of the applied torque. And so in this case, the torque points towards the audience, but it's going to cause the actual wheel to precess around in the direction of the torque. And as we follow it around, that torque vector is always pointing in the direction of that rotation. Yeah, there we go. Sweet.
All right, thank you, Marco, Jake, and Nick. Okay, one more game. Which way will it roll? Which way will it roll? Thank you. Okay, so in this picture, this is me, okay? and I'm standing on this cart, and there's a wall mounted to the cart. It's firmly secured to the cart. And I'm chucking balls that bounce off the wall and go off over my shoulder. The question is, which way will the cart go? Okay? Which way will the cart go? Think about it. Okay, if you think the cart will go to the left, say left. Left. If you think the cart will go to the right, say right. Right. Okay, before I tell you the answer or do an experiment, I want to give you another hint. And I want to see if you guys change your mind about whatever you answered. If I said, you cannot see what's on the cart, it's behind a curtain, right? All you see are balls coming out from the right. Does that change your answer?
No. Yes.
Okay. All you see are balls coming out from the right. Now, which way do you think it'll go?
Left?
I think it'll go left.
Yeah. I think it's gonna go left.
So I'm going to do this experiment, but I'm not going to use balls. I'm going to use carbon dioxide molecules. Okay? I'm going to throw carbon dioxide molecules behind me, and I'm going to see if my cart will go in the direction that I expect. Okay, so this is a very special cart that I made. It's got this cozy chair, and I'm gonna hope that it has no brakes, and it curves very gently to the left, so I'm gonna try to position it just right. And it should shoot not balls, but carbon dioxide molecules behind me if I do this right. All right? So, here we go. Okay, I'm going to hold this behind me. It gets really cold because as the gas comes out, it expands and cools off a lot. And here we go. I'll just use my foot as a brake when I need to. Ready? Okay, I hope there's enough CO2 in this thing. Aww. Wah, wah, wah. Well, I did go a little bit. Well, you know, you can't bat 1,000 all the time. Okay, so that is the which way will it roll. We have one more demonstration for you, and then we will let you go home. And that is the bed of nails we're going to bring back out. Now I'm going to lie on top of this bed of nails. Not only am I going to lie on top of the bed of nails, we're going to make a sandwich. Okay, I'm going to be sandwiched on the bed of nails. And not only that, we're going to put a cinder block on top. And not only that, I'm going to have Dr. Oren Schindel come up, and he's going to smash that cinder block. Now, why will I not die? That's the good question, right? That's the most important question to me. Why will I not die? I won't die because first of all, my weight's going to be spread out over all those nails, right? So the pressure is going to be low, right? And also, when the hammer comes down, the cinder block has a lot of inertia. It's not going to want to move. So not a lot of that momentum is going to be transferred to me. It's going to absorb it all, okay? So hopefully that physics will check out. I am a theorist after all. Take this off. I'll hand you this. Can you advance the slide? Yep. We have dramatic. Did it advance?
I mean, it's just going to the credits.
Back up one.
Back one?
Back up one and then play. Okay, so just to show you that the nails are real, Andre's going to throw an apple on there. All right, thank you guys so much for coming out to the Amazing Physics Show. We hope you enjoyed your evening. I like to do this as often as I can, as often as my department chair will let me, and as often as we have students who are willing to participate. It's a great bunch of students. We worked really hard this semester, and we hope that you can keep your eyes peeled for more physics and coming up in the future. I just want to say that this is the cast. This is our amazing group of students. And I also want to just give thanks to all these folks that helped out along the way. And with that, we bid you good night. All right.